Hi everyone, welcome to another episode of the Haskell Study Group. I'm your host, Ram Vedam with Atlanta Functional Programming. Today we're going to be covering strings and various basic data types available in Haskell, as well as answering some questions that that came out of our discussion last week as well. To begin with, I thought it would be kind of useful first to talk about types in general before we start getting into the basic data types available in Haskell. So what is exactly a type? A type you could think of is like a category of values. So it's kind of a set of values that are associated with a name. There are many types of types that we've dealt with in various programming languages, and a lot of them are already available in Haskell as well. You may have encountered various types for different kinds of numbers, for example, such as integers, fractional numbers, or rationals in some languages. They call them just by their mathematical set name. There are also obviously a type for booleans, where specifically you have two values, either true or false. You've dealt with probably characters, such as char or even string, which is normally a list of characters. Haskell really embraces the notion of having a type system, and its type system is quite sophisticated. While we're going to be delving into just mainly the basic types today, this is kind of the basis for our future discussions into the type system, as well as understanding how to interact with the REPL when actually verifying your types when you're declaring them. To begin with, to explore types that are available, I think it's necessary to understand the notation that Haskell uses to kind of declare that something is of a certain type, or when you're viewing types inside of the Haskell REPL, how it returns what type something is. When you want to query in the REPL a particular type, you'd want to use the :type keyword. This is a specific command for the Haskell REPL. Only purpose is obviously to deal with querying types themselves. 1 second here. Okay. So let's take an example as figuring out what is the type of A. Notice I'm using single quotes around A to declare that this is a value that we're dealing with at the prompt and not a variable. When we do this, we get this kind of notation. We've encountered this notation last week when I was declaring types before, and this is kind of like how you would get the types when you're querying them at the command line. First, obviously, is the value that you're querying for. The second thing is this : which is new to most folks who are coming in from other languages. Usually, you'd use a single colon if you're coming in from, like, say, Swift, when you're declaring something of a type, or you may not have a colon at all, like in languages like Go, or even in C++, the declarations on the left-hand side of the type. What this : stands for is has the type of. So the way you would read this is the value A has the type of char, which is a character, and characters in Haskell include not only alphabetic characters but all Unicode characters as well. It's important to understand that the char is a very generalized primitive type for all alphabetic characters, Unicode characters, symbols, special characters like the question mark, and so forth. If we go and look at, if you want to always, for example, in the REPL, to return the type of a specific value that's being typed at the command line, you can actually certainly do so. You can actually set this up as a default by using the set keyword in the Haskell REPL. Again, this is another command, and to specify that you want to always declare a C to types is using plus T. Now, whenever you type in anything, 5 or A, you'll always get this IT, which stands for it, the value that you provided, and it'll provide the type signature after it returns the specific value. I'm going to turn this off right now, but I thought it's necessary for you for folks to actually know that this exists. And to turn it off, I think is, sorry, not set, unset T. And now if we type in A, we don't get the type signature. We've also actually saw the type signature for functions, where you have a function syntax such as, let's go ahead and load this file up to give you the type of powers of 2. And this is still using the same type signature syntax that we saw earlier, which is variable, except, value, it's going to be the variable name that you're declaring. It's querying up the variable and what the type of the variable is. And it returns this, this syntax here. This is syntax for declaring a function stems from the mathematical notation for defining functions. Basically, what this is saying is powers of 2 has a type of a function that takes in an integer, and the arrow is saying it's mapping to, but you can also think of it as it's returning an integer. Obviously, if you have functions with multiple arguments, the number of input integers you will see is going to be multiple of those. This is a result of the fact that we have a way of currying functions in Haskell. I'm not going to touch base on it right now today, just merely because of the fact that we will be covering it in a later discussion. Right now, though, understanding the type signature of input to output will allow you to start reading at least basic type signatures for functions as you are declaring functions through our discussion today and your continued exploration of Haskell. So we looked at characters with A, okay? But what about a string like hello? Okay, this is a string from a normal, any normal literal value that you may have seen in any language. Usually, it's a sequence of characters and wrapped around a pair of double quotes. When we try to query this in the Haskell REPL, we actually get this definition here, and immediately it'll become apparent that wait a second, something is a little interesting here. You said that it's a type string, but it's treating it as a list of characters. String is Haskell's type alias for a list of characters, and that makes sense because a string is a list of characters. A type alias is a convenient name that you can use to actually declare a type, and then behind the scenes, Haskell will translate it into whatever the type alias is really pointing to, the underlying actual representation of the type. So in the case of string, it's going to be replaced with, in the REPL, with a list of characters. One thing to notice here is list is using actually syntactic sugar for representing a list. We will revisit this syntax later on when we're actually declaring lists in the later part of today's discussion. You could do many things with lists. for example, you could print them. For right now, I will go and say, we can go ahead and say print hello. This is the generic printing function that is available in Haskell, but it doesn't just print strings, it can actually print any object whatsoever. So if we had a function that, what would we call it? Let's say greeting x equals print hello x. I think this will work. What is the type of print? Is it just taking an option? Oh, it's taking a single argument. Okay, got it. So I'm gonna have to do this later. Okay. So what I was going to show you is this can take in any value itself, but I will go and say print obj. Just has an alias for this value for the sake of example. So now if we do print obj 5, we'll get 5. Print obj hello, like we did before, we'll get hello. And it makes sense if you look at the actual type signature for print. What's doing is it's using, again, you can, this is a type constructor that's in Haskell that we will visit in much more detail later on. But you could treat this as just nothing more than it's taking a value A and it's returning this IO function. You will actually, it's actually technically an IO object. It's a monad, but I don't want to really discuss the bigger, deeper versions of what is a monad until later on. We'll visit this. However, the reason why IO is brought up here is mainly because of the fact that when we are, and you will see this in a minute, especially writing stuff to a file, it'll become very important for you to interact with IO a lot. So it's an unfortunate consequence of dealing with writing your stuff to a file versus interacting with the REPL. Given that we have this generic print object, you'll notice one thing immediately. Because it's printing the type itself, the basic type representation, it's actually giving you the string type as is. Okay, it's a literal value with the single quotes. That's because since this is a generic function, it's unaware to dispatch on a particular type to figure out what is the right way of printing this. It goes with the most generic representation of printing the value to the screen. That said, Haskell does provide two string-specific functions, and that is put string line and put string. Okay, obviously put string line will return a new line after printing the string. Notice that the string isn't getting printed with double quotes on it, and put string is just going to do the same thing, but it doesn't actually print a new line. Okay. This actually illustrates one particular thing about some of the function declarations that's available in Haskell, which is that on the surface they may look similar, but various functions could behave very differently based on what type is actually being passed into the function itself, and it dispatches accordingly to the underlying function logic that needs to go in and execute that code. So we're now at a point where I can actually introduce the Hello World program that is pretty typical for most folks when we're starting out in programming languages, and that's this function here. I'm going to show this to you in the file in our Haskell, in our stack project that we created. just a review of this file here. Haskell kind of now, otherwise this will throw an error when you're especially compiling, kind of expecting you to first have the module declaration here. We have the module name, and where is like where all your obligatory definitions are going to go. Now we have obviously a main function here. Now Haskell does use main for especially when you're building executables. Building executables is not actually necessarily loading the file into GHCI. It's actually running GHC against it, and you'll get your standard binary that you would if you for example compiled something in say like C++ or C. And the way it does it is it actually looks for this main declaration, and then it will go ahead and execute it. There's no way of actually specifying which function is your entry point. This is slightly different than some other functional languages that we've covered here, in particular Common Lisp or even Scheme, where you could actually specify what function should actually be executed when the quote-unquote Lisp image or Scheme image loads up. This is very important to keep in mind because when you're building applications especially, you might get into some bad habits if you're just interacting with the REPL, not realizing that you're getting into, you need a main executable when you're ultimately ready to get a binary. So one suggestion that was kind of made from some of the stuff that I've been reading is just maintain kind of a single top-level function that, file that will keep your main entry point. And then you can normally interact with the REPL by just doing simple, load the file into the REPL, and it'll work just as is. And in fact, this will work as is too as well. It will actually load our main function into our REPL, and we can actually go ahead and run it. Okay. A couple of things here that we need to kind of break down bit by bit. One, obviously, is because I introduced I/O here, I think it's important for you to understand what it is. It is a special type. It's necessary when you are especially running programs that are going to be involving side effects, and side effects includes even talking to basic I/O devices that are in the host operating system. So like talking to standard out, standard in, standard error, even like reading and writing from a socket or reading and writing to a file. Like any I/O whatsoever is considered a side effect. So when you are dealing with those types of operations, you'd want your function to actually go and return this I/O type, and then do whatever necessary things that you need to do in order to execute those commands to do the effects that you want to do. Now, the main function itself also introduces one more thing, which is this do syntax. What does this do syntax do? Do actually is a syntax that allows you to write sequential actions. So it's essentially running various things one thing at a time. Let's say, for example, we replace this guy with, just typing in a couple things like hello, and then you could, use a combination of, so let's do something like welcome to the, and this is obviously a contrived example, but it will illustrate the point. Let's do this. Study. Okay. If we run this guy, you can see that it is running each action like it's a sequential program. All right, so it'll allow you to run the commands one at a time. All right, Normally, obviously, in a functional programming language, you would, as many of you know, since we are dealing with immutable actions in a lot of cases, the ordering in which a particular action occurs may not necessarily be the same during execution. And a lot of times, the REPL or compiler will try its best to see if it can run a couple of things concurrently. But in this particular case, especially since you're using the do syntax, you are actually explicitly telling Haskell that this code, this function, is running the following things in sequence. And you will see this used a lot when you are especially doing stuff with side effects and you want to be able to control how those side effects are executed. We'll revisit the I/O type later on in a lot more detail, but this is kind of the basic idea for folks who want to start writing like basic executables. You could certainly use this, and you'll be okay with it. There isn't a whole lot in terms of some of the errors, at least at the basic level, that you'll encounter if you're just running with this right now. And obviously, in this case, we are not dealing with input yet. When we revisit I/O, we'll also deal with about reading input and, from within a Haskell program from standard in. So let's talk about string concatenation. Give me a second here. Let me just go back to my previous tutorial file. String concatenation, as with any language, has actually, let me make a new file here. Make things a little easier. Tutorial. One second. That's thing up. Okay. And we're going to go ahead and use I/O for a minute here to make another program out of this. Okay. Okay. So to concatenate, as many of you know, it means kind of linking together all the different things that we're passing into the concat function. String concatenation in Haskell has several approaches in terms of how we can actually concatenate strings. In the first case, and let's start with the basic hello world string. Okay. And again, notice I'm not using the list syntax, I'm using the type alias here. We could just simply concatenate with the infix plus plus operator. Okay, the plus plus operator basically, if we look at the type here, and remember, if you're looking for operators, you need to wrap it around parentheses. You'll see that it'll take a list and another list and return the list. This actually goes and concatenates those two strings and makes it and returns the actual concatenated string upon completion. Another way of doing this, though, is to call the concat function itself. And I'll show this through another contrived example here. But let's say that we have two strings that we've defined here. Okay, world, and in here we'll go ahead and put string ln, and you know what? Let me do this to know the difference between the two. 15. And we get hello world here, or put string ln greeting, and we're going to use where here, which is which I introduced last time, to a way for you to lexically define a variable. And we're going to use the concat keyword. Concat. And we could now, this guy, just to give you kind of what it does, it basically takes, it's a reduction function that takes in a list and then creates a list here. A type of a specific list, at least. What we'll do here is it will pass in hello, the space, and the world has a list of strings. And when you write it this way, it's going to go ahead and use this as a top-level expression to use those variables by doing quick lookup. Although it looks like there's a particular error here. Image, blah, 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 expected type string. Let me see if I can do this. Oh, that's weird. I'm guessing it doesn't like the fact that I had it all in one line. Okay. Let's do this, and let's run our main function now. And you'll see that these are two different ways of concatenating strings. One might be necessary than the other, especially if you're doing if you're getting a bunch of strings or a bunch of objects that you need to get concatenated. You might want to prefer the concat operator, the concat function versus the concat operator. So knowing that these are both available is pretty useful. Since I talked about top-level expressions versus local expressions, I'm going to dig into a little bit deeper to what I mean by that, just because this is particularly useful to know, especially when you are dealing with files, because when you're dealing with files, it becomes very apparent as to what is something defined as a top level or something that's defined locally. Okay, so a top level declaration is when you're loading in a file. Okay, it will basically read these files. Okay, and every bounded variable, all right, bound variable that it finds and it also checks to see if there's a type signature. This is one of the reasons why, if you recall, if we don't specify a type signature, you will get a little warning saying that top level binding has no type signature. It kind of expects that the type signature is being there because when it's reading it in, it's kind of enforcing that type signature upon after the parse to make sure that the values kind of match at what is declared. So it's using this stuff here to actually go in and verify, type check all the basic values, and then load them up into you could think of it like a symbol table that will ultimately be used for querying later on when something is actually being retrieved. These are scope-wise at you could think of it at the module scope. Okay, so that means at the topmost level scope that's available for the program. You can reference these anywhere else. In fact, if you're shadowing them in the file, as we saw last time, it'll actually recognize that the top level binding exists, and it will mention to you, by the way, this variable that you have is already referenced earlier in the file. Be careful, otherwise you might end up getting some unexpected results and things like this. This is slightly different than something that is lexically defined, and we've talked about lexically defined variables last time with the let expression as well as with the where expression. As you can see in this case here, greeting is not necessarily defined at the top. It's actually not defined at the top level, and we could see this by just typing in greeting and getting an error. Okay, the variable is not in scope. But within the scope of this definition here, it is, and you can see it in clearly here in this particular case, because we're able to actually figure out that this is not a top level value. Top level values also can be split across multiple files. And you can reference them in other files by using their module name dot whatever the file the value name is. We'll see more of that when we're covering some more advanced features and we start writing more projects. But it is something to be aware of, that there is a clear definition and clear difference between something that's a top level expression versus something that is locally defined. So if you see something that's defined in where or in let, just be aware those are lexically scoped. They're only available within the scope of that function definition. Whereas with definitions that are defined at the module level, those are top level expressions that can be referenced anywhere within the file, or if you define them in the REPL as well. Any questions on this? Okay, so we talked about okay, so let's go back to and dig a little deeper into this concat function here. As we saw before, our concat function takes in a foldable and and a list, and it returns another list. Okay, it's important to know what this foldable t of list is actually doing. In older versions of Haskell, this used to be defined as, or would be displayed as, essentially list of lists and returning a list. Okay. Foldable T is basically kind of like that too as well. It's anything that can be necessarily foldable. It doesn't necessarily have to be a list. It could be something else. But it's bringing in that foldable representation of that contains each element, which is of type list, and then it flattens them. Okay, so that's what this concat function is doing compared to the concat operator, which we saw was just simply the list that takes one list of A and another list of A and then returns a list of A. This is a binary operator that or a function that it has an arity of 2. This is very different than this one, because this can have multiple arities, because it's as long as the underlying single argument, it's actually to be more precise, a function that takes in a single argument and returns a list. But that single argument is of type foldable. Again, the foldable is another type of type class, much like IO is another type that you'll be encountering. I don't want to introduce type classes just yet, but just be aware some of the literature that you're going to be reading, or if you encounter this, will mention that this is of a type class, so I may as well go ahead and mention that it is a type class. The other type class that we saw earlier was show as well. Show is another type of a type class that you will encounter. And that's basically something that, as long as there's a way to display the object, you can go ahead and execute the function. But that's all I'm going to mention about that, just so that I don't overwhelm the audience, and I don't stray away from what we're discussing here today. Concat not only can concat strings, but it can concat anything because it's just a list of lists, as you can see by this definition. And we could see that when we go ahead and use this for, say, for example, concatenating a list of strings. I'm sorry, a list of integers. Okay, and this list of lists doesn't necessarily have to all be the same size. It could be like this, and it will go ahead and run the proper concatenating function and flatten every single list into a single list structure. Since, as I mentioned, string was a type alias to a list of characters, that's the reason why concat can actually be worked on a list of strings, because it's just thinking of each string has a list of characters, and it could run the same reduction function. So again, to review this function here, the difference between concat and foldable is this is a single argument function that takes in an argument of that's a foldable set of lists. Well, a list that are stored in some sort of foldable structure, and it returns a list has a result. Whereas with the plus plus operator, the concat operator itself, it takes in two lists, as you can see here. The first is, and we could read this function signature as, I take in an argument that is a list, and I return an argument that is a function that takes in another list and returns a list. Okay, so folks who are still getting used to this syntax, you could think of this as being equivalent to, I don't believe this is going to work, but we'll see, the following. You can add parentheses here, and parentheses will be right associative here in this case, in this syntax, because we're basically saying that it's taking a function as an input, and it's returning this function as an output. It's applying the variables that are passed in during the mapping from left to right. And once all the variables are bound, then we'll go ahead and execute the function. So this syntax here is just an example of a curry function without actually delving into other details about it. The one thing that you may notice here is, just like the foldable syntax, we have this lowercase a. Okay, it's not actually explicitly saying strings. Okay, that's because, much like the concat function, the concat operator can actually work on any two lists of arguments. Okay, regardless of the type. This lowercase a is what's called a type variable. It's generic. You could think of it basically saying this function takes any type, list of any type, and it returns a function that takes a list of any type and returns the final list. Now, you might be wondering, now the first thing, well, this is a generic type. Does that mean that I can, try something like concatenating a list of integers with a list of strings? Well, I hate to break it to you, but no, you cannot. Because what's happening is this signature is saying, although it's a list of any type, it's not saying that the first list can be of one type and the second list can be of another type. It's saying both lists have to have the same type in order for this operator to actually get executed. So this is a little, what's it? For folks getting into the language, this is a little bit of a learning curve that you need to get through, and a bit of a hump that you'll have to get over. Just because, yes, it is saying any type, but the signatures is actually telling you that there is a constraint here. It can be any type as long as the two lists are the same type. Okay, and there are other function examples that you will see and you'll encounter that are that can have two generic type variables, but as long as they're different types, it doesn't matter. But for now, just be aware when you're looking at some of these operators, especially the string concatenation operators, they are expecting everything that's passed in to be the same type, which in this case is of type string. The concatenation operators, especially since they're generic. Okay. So one thing to notice about this, that if it hasn't become very apparent, is that these operators are, because they're generic, and they can take in any type. This function is an example of what we call a polymorphic function. Okay, let's remember what polymorphism is. In polymorphism, if you recall, in a lot of object-oriented languages, especially if you have a type hierarchy, a polymorphic function will allow you to pass in an argument of a specific type hierarchy, and as long as there is a method defined on that particular subclass or that subtype that can be dispatched on, the underlying compiler will prefer the dispatching on of the more specific function call versus the base class's implementation, if it has one. Okay. In some languages, for example, you might have what are called pure virtual classes, and C++ is an example of this, and that's their way of implementing like interfaces, where each function has to have a subtype that has some sort of implementation for a function. In Haskell, you don't necessarily need to do that. In fact, you're decoupling the representation of the data that you're representing from the actual algorithm here, as long as you make sure that the constraints that are being passed in all match at the time that it's being executed. And when that happens, if it's written this way, as long as the main type constraint is matched, which in this case means the two lists that are being passed in are of the same, have members that are of the same type, this code will be valid and will execute itself. Okay, and we'll encounter other examples of this as we keep working through things. Let's actually see the specific error that we saw earlier just one more time. Let me see if I can actually go up. Control P. No. No. Go. No, doesn't look. Oh wait, I go. I was in model. There. So the error that we're getting here is saying the first argument arising from the literal is not a type constructor that can take a number and a string and then convert it, okay, for this literal. So in this case, what it's trying to do is it's trying to take 1 and it's trying to construct a number from a string, thinking that 1 is a string, but 1 is not a string, right? So it doesn't match up because what it did is it recognized that the second argument for the concatenation operator is a list of lists. And if you recall how currying works, is it's applying each function. It's binding each function one at a time. So each input in the function one at a time. So in the first case, we'll bind the list of integers, okay, and it is now expecting technically a list of integers and returning a list of integers. However, since it got a list of strings, it's going to attempt to type construct an instance of a number, and in this case, there is no type constructor that could type construct from a string to a number right now. So it just throws this error saying that there's no instance of this expression because it couldn't implicitly convert this to an integer before it can do the concatenation operation. We'll see something even simpler if we do hello. And we try to concatenate it into 1, 2, all right? It's going to be the same idea, except now we're saying that we're taking in a list of characters and we're also taking a list of numbers, and we'll get the same error. Now it's attempting to construct a number from a character with a literal 1 in the second argument. So regardless, it's going to, since you can't convert either or type, it's going to throw up this error. So just in general, keep that in mind when you're debugging some of your signatures. It actually tells you what it's attempting to do when it's executing in the error message in GHCI. And that's because GHCI is essentially asking for an instance of that numeric type, and numeric, this particular thing, I should mention this here. This num is also a type class, all right? One thing that you will notice in your early experience of writing Haskell code is, although you yourself are not using type classes explicitly, because we're not at that point yet, a lot of the underlying standard library and standard library functions heavily use type classes to enforce types before they execute code. So just be aware of that. To briefly define what a type class is, just because again we'll be digging into it later on. It basically provides a set of definitions or functions and that can be shared across different types that you might have. So you could think of these as constraints, higher order constraints on a particular set of types, okay, that you might have defined, concrete types that you might have defined. We will encounter this and dig into it much more later. But for right now, all you need to understand, just because it's going to help you understand the error messages, especially that GHCI gives you, is that these type classes do exist, and what's actually happening behind the scenes is attempting to verify the inputs of the argument so that to make sure that the type classes that are required all match up, much like the types match up, before it goes and executes the function. So just like all of our other operators, it might be useful to know that you can also write the plus operator as in prefix style. So it could take in your 2 arguments and then obviously run it. The other thing that you should be aware of is because you can go and prefix it like this, we can actually write our concat operation here has plus plus hello with an infix prefix plus world, and what will happen is it's going to emphasize a different associativity. Here, in this concat example, we're left associating and we're folding, essentially doing a fold left. We're starting with hello, we concatenated with the space, we're then concatenating with world. Here, we're going to start with world, we're concatenating that with space, and then we're taking that result and concatenating that with hello. by using just the prefix versus the operation, infix operation, you're changing the associativity of the operator for some of the operators, and in this case, where the the concatenation operator changes its associativity. If we run this, you'll see it will still give us the same result, mainly hello world, but the actual execution has changed. We can actually see this if we go and look at the concatenation operator. Remember, in order to look at the concatenation operator, you can actually use the info, and then, or :I, and it'll give you the same thing. You'll see that it is technically an infix operator with right associativity, with this precedence of 5. Since where provides and creates lexical variables, if you attempt to concatenate anything outside of lexical, actually, let me rephrase that. Where is a special lexical variable binding clause? In this example here that we've introduced here, where is actually bound to the expression that's directly previous to it. It's bound to the actual expression itself. Okay. If we were to simply reorder this code here, okay, you might think, oh, this probably will work, right? And what? That's weird. Hold on a second. I may have done this wrong. Yeah. Sorry, not this one. You might be thinking that, well, since where is already defining greeting in this lexically scoped area, this function itself, you might be thinking that, oh, you know what, that means any function that calls this might treat where as part of the global environment. So I'm thinking of, in the case of like folks that may have encountered this in like using closures, okay? So you have a lambda function that, if you remember what a closure is, you have essentially some environment variable at some top level, and you created an anonymous function that uses that that variable at the top level, and it encapsulates that bound variable when you run it, and now it's within the state of the expression that you're encountering. Okay, so if we create another function that uses a lexically bound variable, one might think that this is going to be okay because we've defined the execution of this in the actual environment where greeting was actually defined. But that's actually not the case, because the way Haskell works is this is considered 16 through 19, okay, is considered a top level expression, right? So it's expecting anything that's used, any bound variable that's used, to be already defined either at the top level, or you're going to provide a locally executed a locally defined variable using either where or let. Okay, and although I did not even load this, you will get this error same as what we're seeing here. One of the nice things about using at least Dante environment that's available in Emacs is that it does real-time compilation and loading, and it'll give you these warnings ahead of time before you load them into the environment. And we can see this with the red squiggly lines here. That's saying that it's a warning, variable not in scope, and it even furthermore infers what type you could see here. Versus what you might encounter there. So bottom line, if you're creating top-level expressions, you cannot use variables that are not either lexically defined within the scope of your own function definition, as is the case in main, or you are using a variable that's available at the top level, like as in world here in this example. So this is just being aware of what is going on. Okay, there's one comment, whatever type is. Right. Okay. There's one comment about one of our earlier things in the live stream about character A is the type variable A. The one the comment was related to our signature here, this type variable, and the audience member mentioned that this type variable A, at the time that it was bound initially, it must remain consistent for the rest of the representations that it sees inside this type signature when after every subsequent substitution. And this makes sense because during the type inferencing phase if you notice that something is an int, you've already now substituted. You got to think of this like a beta reduction. It's like lambda A with all this stuff. It's saying this is of type int. So now all these have now suddenly changed from A to int, takes another int and returns a list of ints. That happens after you parse it. So thank you so much for mentioning that, and you're right for regarding the type signatures there. It would be important to go through that. Okay, so we're almost through this. Just a few more questions, the operations, and we will. I'll take a small break for questions. So since string is a list, okay, for all intents, for technically speaking, it's just an alias for a list of characters. You can actually use all the standard list operations that are available for Haskell to work on any list on strings as well. Okay, so an example of this, I think the easiest way to do this is just to go ahead and create a new file. Let me go ahead and create another file called list.ops.hs. Okay, and list examples. And in here, let's go ahead and create our standard IO, just so that we don't get any complaints from Haskell saying that there's no main function in this file. Let's create a simple string, shall we? Let's again, we could Haskell Study Group. We'll call it Haskell Study Group. Okay. And obviously, since I need to declare my string, we'll go ahead and do that. And we do that, and we load it. Now if we look at Haskell Study Group, okay. Now I will say just a couple of interesting things. One is that this single character quote versus double characters do change the type. So be careful when you are writing your code with characters explicitly. I'm just showing that now because this is going to become important when we are going through these list operations. Okay, so the first operator I'm going to show you is the cons operator, and yes, it's cons, C-O-N-S, following the list parentage. This is an operator that is represented by a single colon. So if we look at the info of single colon, you can see that it will take any type and it will concatenate those types. Okay, it is a right associative infix operator. What it will do is it will look at the base type. Okay, we look at the signature. Okay, and the list of types, and if they match, we'll go ahead and concat those operations based on the location that you're putting it in. So an example of this is, let's say that we have a single character H, okay, and we're trying to concatenate it in the beginning to Haskell. It will recognize that H is a character, Haskell is a string of characters, okay, so it's a list of characters. These two match, okay, now we can go ahead and concatenate. And you can concatenate any even empty strings like this. Okay, as long as it recognizes that it's a list of characters, you're good. And you can see this when you do type of the empty string, that it's expecting that it's a list of strings. It's just the double quotes is literally syntactic sugar for constructing a list of characters represented as a string class. Okay, this is something that just to be aware of. Once you have a string, like our Haskell Study Group string here that we see, okay, we can actually start asking for things like the head of the Haskell Study Group, all right, or the tail. Okay, this is like car and coulter for folks who are coming in from Lisp. First and rest, if you're looking at other languages, I think Clojure uses first and rest. Don't believe there's something equivalent in some of the newer functional features in other FP languages. Folks who are aware of those, let me know. I'll post and list them out. So tail gives you the rest of the string. You can also treat this, even though this is a finite string, you could actually grab substrings of this, starting from the beginning using the take operator. So let's say that we want to take the first two characters of what this represents. Okay. You can also take 0 characters from what's available, and you get the empty string. This is kind of just interesting to be aware of. Now, there's also the drop operator. Drop basically allows you to drop a certain number of characters starting from the left side. So in this case, if we want to drop the first 3 characters of the Haskell Study Group string, we can certainly do so by doing drop 3 Haskell Study Group, and you'll get called Study Group. Now, did that actually change the Haskell Study Group? Well, no, because again, all variables are immutable coming in from a file once it's loaded. These aren't actually being redefined inside of the REPL. Just to review, in the REPL, you can actually technically redefine your variables, although when you ultimately move them over to the file, they'll become immutable by default, because upon loading it, it makes sure that it doesn't, bind two things twice. We've already seen the concatenation operator, which is also a list operator itself. But there's also another operator that allows you to grab the element at a specified index. So if you treat the list of a list as a randomly accessed collection, you can actually go in anywhere in the collection and actually go and return a value. We can go and look at this operator and see that it takes in a list of any type, an integer, and it'll return a value of that type. Okay, this operator, again, you can use it in prefix or infix style. I'm going to use it in infix style. We'll take in indexes starting from 0. So these are C-style indexes, not 1 for those of you coming in from those languages. And it'll go ahead and return the value. So if you ask for the first value, you will get the first value. If you ask for the fourth, again, which is actually technically 3, you'll get K, and so forth. I mean, these are accessible for you to go and query your lists. One thing, and I think the best to illustrate this is one thing to note about these list operation functions is if you're dealing with empty lists or any lists, you're going to get exceptions thrown. It is not going to it doesn't handle any empty lists at all, and that's because in Haskell these prelude functions are considered technically unsafe. They are unsafe, which is kind of weird, but there are versions of these functions that are safe, and we will, as we start moving in exploring lists more deeply, you will actually be aware that there are safe versions of these. I think it's called safe head, safe tail, and so forth. But I won't address them now. We'll see them later on. One thing is to note about some of these functions is because that they are empty, they are unsafe. For any real-world program, it is recommended that you try to look at safe versions of these. And again, when we address some of that, we'll see how that can all work. So I'm gonna just stop for a minute here before I start quickly firing off all the other basic data types that are available and ask if there are questions. Let me give me a second here so I can go and look at the stream and see if there are questions.
So I have a question. I'm not really clear about the prefix operator when you were writing the function. So how does it know, that you want to do a prefix? Is it just if you put the plus plus in front, that's how it knows that's a prefix?
Are you asking? Okay, so you're asking the difference between prefix notation and infix notation. Okay.
Correct. Yes.
Okay.
Yeah.
So there are different types of ways of technically calling a function. Okay. Prefix, infix, and technically postfix. Different programming languages support one or the other, or sometimes both. In the case of Haskell. Or all three, but I've rarely seen a situation where you can actually have all three. The difference between infix and prefix, which is what you'll often see in Haskell, is the location of where the operator is going to be located. Okay. Infix normally you probably encountered a lot. If you're looking at standard mathematical notation, the fact that the operator is in the middle between the two operands, 1 and 2, the plus, that is a way of performing an infix operation. Okay, that's the infix style. It's basically parsing it, recognizing that this plus needs two arguments that are around it, surround it, and then it requires those two arguments to be available in order for that function to execute. Okay. Prefix style is something that you already know. Most people already know. They just don't realize it. Okay. When you actually call a normal function, say f of x, okay, in any like programming language, whether it be Python, C, C++, or what have you, you're technically using an infix style, a prefix style way of calling the function, because this function is the first argument in the expression, and it's requiring the rest of the thing to the right of it to being arguments of this. Okay. So what does that mean for operators that can be used as a prefix operator as well as an infix operator? So when you are using this function, let's go back to plus here. If you use plus with parentheses surrounded it, and what this is telling the Haskell compiler and even the Haskell REPL is that look up the function that's associated with this operator and call this function on these arguments. Okay, and what it will do is, oops, sorry, I forgot that this requires only two. I was thinking of Lisp, and this function here that takes these two arguments, it binds them to the function that it looked up in the first one. This plus operator, and it then calls that function directly. Okay. This is different than this. This requires a little bit more work in terms of what's happening behind the scenes, but ultimately the result is the same. I know you may not have encountered this ability to take an operator and go into the prefix style, but the prefix style is very natural if you just think of it like, I'm going to treat this as calling a function, because that's the syntax is exactly the same. Okay? Does that make sense?
Yes, yes, it does. Thank you.
No problem. Okay, there is a question. Regarding integers to a string. Okay, so there's a question regarding how to convert integers to a string. You're jumping ahead. I'm just about to cover that. So just give me when we're covering numbers. I think we'll be covering that too as well. So hold on. Our journey is still going on. Okay. Okay. So what we've encountered with types is, although very specific up until, very special up until now, because we were dealing with strings mainly earlier, is just by the declaration we are improving the actual, um, so-called, safety and maintainability of their Haskell code, because they are actually limiting the types of data that are being passed into, the programs, and they're a way of allowing the Haskell compiler to itself go and, what's it do some precondition checks to make sure that certain, static variables and static data is already, you know, uh, correctly being defined in order for the program to actually execute the way you expect it to. And this is just a style note, but for some folks, they there's a claim that, it also improves the readability of the program. Um, I think that style is obviously, in the eyes of the beholder. Some folks, like writing a lot of types. Other folks just kind of expect the inferencer to kind of like kick in and figuring out what those types are. Um, and obviously Haskell has some inferencing, but we'll step into those, later on. Types, though, are more than just what we've kind of encountered, and we're gonna, kind of build up to, some other types, right now. But they provide the means, essentially, to, because of their corrective nature, to build programs, a lot more quickly, because you are, getting rid of a whole class of bugs dealing with, that you often have to deal with at the runtime. I'm especially, I'm thinking about, those, folks who write, large scale, Python code and have to deal with like certain very subtle runtime errors that turned out to be because of a type error that actually happened, later on, earlier on, but they didn't recognize it because they didn't execute the code, and you know uh, it only shows up when you actually run the function call, and it's like, oh, I don't know what's going on here, and it takes a little bit more debugging, which is a bit more challenging. Um, it becomes more useful though later on, when we're dealing with other, data types, because, over time, as you're building up your quote unquote types, in your higher order types that are built on these primitives, whether they be called structures or what have you. I mean, there are different names for this in Haskell, and we'll see some of these, um, later on. uh, you'll end up realizing that, you'll be doing a lot more things with a lot less code because of function composition and the ability to actually, verify that the types all match up. Okay, and we'll see some of this, right now when we're looking at, some of the additional types that are available in the language. We've already talked about characters and lists of characters last time, earlier with strings. We also introduced numbers. Now, I didn't completely cover all the numbers, and we're going to be shortly looking at those. But I just want to mention, briefly that, it doesn't just include integers. It doesn't just include floats and doubles. Most of you probably know from, whatever languages that you're coming in from. Haskell does provide a lot more variety of, numeric types, and we will, touch base on some of those. The first thing to be aware of is up until now I've kind of hand waved over what, types are, and, how they're associated with values. I mentioned that types are essentially sets of values with something in common earlier, but that doesn't necessarily also, work well when you're talking about Haskell in general, because in Haskell everything is an expression. Okay, including things that return a value. Those values are essentially an expression that's being returned essentially to a value. The value that's actually being returned, that thing has a type. Okay, so when you look at an expression, all right, let's say x equals 5. Okay, that notion of the expression is, you can think of that like const function that take in a 5, and regardless of what value that you're returning, in this case x doesn't need to take in anything, it will always return 5. That 5 has a value of whatever you define it to. Okay, so if we look at 5 here, if you remember, it is a numeric type here, where num is a type class that has certain properties associated with them. Okay. This type class here is somewhat abstract. It is a set of concepts that are kind of defined at the time that you define the type class or you define the concept. And those are actually enforced when the code actually uses this particular value or this particular variable that ultimately returns this value. Okay. The best way to really keep track of this, honestly, is just to be aware um, uh, that these are sets. And if you think about sets in types as being sets, it will help guide your intuition a little bit more, at least with respect to a lot of the primitive types that are available in Haskell. Okay, I know that's a lot to swallow. But just keep in mind, if anything, that types, particularly primitive types, can be treated like sets of values. Okay. Let me go ahead and move this here, move that here, just so that our main is always the last function in this file. Here, let me go ahead and do this. Okay. Now, this obviously is hand-waving thing because there are a lot more things related to Haskell types, but this is probably the easiest thing to just keep your head straight, head on straight, just when you're looking at some of these types early on in your Haskell career. At least that's how I've been so far dealing with them, and I've not yet hit an encounter where the special definitions are required. Okay. Okay. So when defining a type, okay, you're going to be ultimately using something called a data declaration. Okay, and this is a notion of this is a type of definition that you could think of as a type constructor, and this is often used when you are defining functions and function signatures. Okay, as a simple example, to really provide some concrete explanation, let's just write our own boolean, okay, defined as an existing boolean, okay, just to look at what this is. All right. What is this? Malform head or type? Oh, sorry. So that's the first rule. Data definitions or data declarations have to have a capital letter in them. Okay. It won't allow you to have lowercase letters for this type declaration. They are there. It's a requirement. When you're reading type signatures, you're going to be using this kind of declaration, specifically the thing that's here on the left-hand side. The values that are specified here on the right-hand side, the definition of the data declaration, they inhibit the type that's being defined, specifically in this case, my bool, right? These also are technically data type constructors that are going to be, well, in this case, they're data constructors that when you're constructing a type, it'll recognize it's going to be either being a false type or a true type. And these guys have their own definitions that earlier on have been defined. In this case, we're using standard types that are available inside the the Haskell prelude. All right, and this represents the set of valid types that will be of type mybool. Okay, so let's actually go look at and deconstruct what this definition is actually telling us. Okay, the first thing is the type constructor, which in this case is called mybool. Okay, this is when you're using this in other definitions, you are ultimately going to be using this to actually go and it will ultimately recognize by the Haskell type system as a way to construct these types, especially when you're using them as arguments to functions. Okay. The second thing is that you're looking at is the first data constructor, okay, that is available for this type, okay, that's false, all right. Now, this will construct false values, okay. So the difference between a type constructor and a data constructor, and you're going to see in some cases that the type construction and the data construction are named the same way. This threw me off when I first, looked into Haskell, and I know it will throw off other people, so I'm going to try my best to make sure that this is clear here. But a type constructor is defining a set of one or more types, okay, or in some cases, if you're doing a type called a product type, it could be a concatenation of one or more types, and you associate a name with that rule. That's what a type constructor is, okay? A data constructor is if you're creating an explicit instance of a value for that type, okay? So in the case of false, that you could construct a false value by just passing in false and some other value. In fact, you could look at that by just doing info false, and you could see that it is of type bool, and it tells you that it could take in anything. I don't think I may have done this wrong. Give me a second here. Let me look at that info again. Okay, so it's not a function. Okay, this is a type constructor. It doesn't a type constructor that it doesn't take in a value. So in the case of Booleans, I just learned this right now. I assume that I could pass in anything that's a false value here, but Booleans are properly defined as essentially type constructors that don't take in any values and then can construct an instance of that type. Okay, there are instances, and we'll encounter this of data constructors that you can construct by passing in arguments, but this is not one of them. It looks like so. I'm going to have to come up with another example on that later on in our discussion. The pipe syntax is something also that is important to be aware of. So this pipe syntax here is what's called a logical disjunction, just like from an OR from Boolean algebra. But what it's doing at the type definition level is it's creating what's called a sum type. Okay, a sum type is nothing more than saying that this higher level type, mybool, can be one of these other subtypes. It can be either a false value or a true value. Okay. You can have some types of various complexity But the idea is you could think of it like like a like a union structure inside of a programming language where you can hold a value of any specific type, and there's a tag that tells you what type it is, and based on that tag, you actually go in and interact with the data in a particular way. Okay. Um, uh, for folks coming in from languages like, say, Python or something like that, you can mimic this kind of idea by using, say, a class that has a ID, has the tag ID telling what type it is, and then you can introspect that, and based on what value that type ID is, you can go and interact with the actual data that you're holding any specific way. A lot of languages that use introspection can do this as another way of doing some types to do type-oriented dispatch too for function calls. But again, this is probably the clearest notation for doing like some type definitions, because you're basically saying this data type that we've defined can be one of these other subtypes using logical or logical disjunction. Okay. This entire line here, the reason why I'm dissecting this is this is a data declaration. Okay, this entire line is called a data declaration. Okay, they not all data declarations actually follow this pattern. They're not all sum types. You might have product types using logical conjunction like ands, and that's usually with them concatenated together, and we'll see some examples like that. But if you see in any sort of real-world Haskell code a data with something like this, some definition and some rule, you could basically treat that as a definition of a type that's going to be used later on in some function declarations. Okay. Let me just go ahead and write this. One or more type of data constructors, e.g. written using logical disjunction, which specifies a sum type or logical conjunction, which specifies a product type. And we'll see an example of product type later on. But as with anything, you can actually go and query the REPL to get some of this information about, the types that are available. So in the case of, instead of my bool, in the case of bool, you can actually do info bool, and it will go ahead and dump the actual rule that defines the bool, right? The data declaration that defines the bool. So it's really useful to be aware of. Okay. Not say text one. All right, that's right. Okay. Okay. So the use of data constructors and the use of type constructors occur depends on what you are trying to do. If you are declaring a function, for example, you are going to be using the type constructor to declare a function. Okay, and what I mean by declaring a function is declaring the type signature specifically. Okay, if you're writing the type signature for a function, the inputs that you're going to have is going to be the name of the data, the type constructor that you're actually taking in as input, and the type constructor that's going to be returned as an output. Okay, so the example that one example that would become useful is looking at maybe like say the not function. Okay, the not function basically takes in a bool that's a type constructor bool, and it returns any value that's of type bool as well. So again, it'll return, it'll in its function declaration, okay, in the actual type signature of that function, it's going to use the type constructor name to actually determine what values you're actually going to be dealing with. When you're actually calling the function, though, you are actually creating instances of the data using the data constructor. So like in the case of not, you won't actually say not bool, right? You'll get an error like this because it, actually let me show that again. It specifically says that the data constructor is not in scope, and that's because there is no data constructor named not. Okay, I mean, sorry, there is no data constructor named bool. You can actually look at that in the data declaration. The type declaration explicitly says that these other data constructors are what you need to use to construct something of type bool. So what you'd want to use is the actual data constructor name that you've specified in the rule. So in this case, either false or true can be are treated as bool. So we can either use false or true in the data construction, and will return true. I mean, sorry, true or false depending upon what you passed in. This is very important because this also is related to results of functions. So like in the case of an expression, let's say like a predicate expression like 4 is less than 5, okay? What it's actually returning, all right, is going to be the data constructor true. And since that data constructor is defined as being of this type constructor bool, the ultimate thing that's going to be returned in the type signature when you query that expression's type is bool. Okay. This becomes very useful when you are trying to match up types. All right. You know, this is which is why I'm spending a little extra time on this, because what actually is the value is the data constructed value, and what is actually the type is what does this data constructor match to, okay? The name of the type that this matches to. And we'll see more examples of this, but I hope that particular piece makes sense. One moment, I'm just going to take a quick drink here. Okay. So, as I mentioned, Haskell has many numeric types. I'm going to briefly mention the majority of the ones that you'll see. They go under essentially 3 major categories: integral numbers, fractional numbers, and then essentially then you have your floating point numbers, which includes floats and doubles. Okay. To start with, we're going to start with int and then integer. Okay. Now you might be wondering, well, wait a second. You're saying integer is slightly different than int. Yes, you could treat essentially an int as a fixed precision or fixed num, all right, integer. It has a range with a minimum and a maximum, It cannot be arbitrary large or small, which means it doesn't handle big nums that are in that's normally available in like or big decimal or anything like that. So int is your fixed precision integer, right? For your numeric types. All right, fixed precision integer that has a min, max, valid range, and cannot be arbitrary, large or small. Okay, so that means it could overflow. You could, if you end up using int. So if you write a function that says f colon int arrow int, okay, what you're basically saying is really to the person is this function kind of expects that we're dealing with small numbers or numbers within this valid range. It could be a I'm not entirely sure what the maximum of this is. I was trying to figure that out earlier, how to get the max. I think later on I have some notes on that, but long story short, this can overflow, okay? If you want something that could promote or deal with arbitrary large numbers, you want to use integer, okay? Large or small. Because there's overflow or underflow in that case. Integer is what you'd want to use for arbitrary large numbers. Very large or arbitrary small numbers. Okay. Just because there you have a much larger range, it will recognize that it needs to deal with a much larger size, and it'll make according benefits to actually go make sure that those all match up. Okay. There's also word, which I found out the other day, and this is another type of fixed point integer, fixed with fixed precision. The lowest possible value for this guy is 0. Okay, so you can think of this as your unsigned integer in Haskell. Okay. So because the lowest value of this is 0. So I kind of like think of this as an unsigned int. Okay. I don't know necessarily if it's. It doesn't look like it has an arbitrary large number, but it definitely gives you an unsigned range. So it's from 0 to whatever int max is. The next type is obviously your fractional integers, which include fractional numbers, fractional numeric types, which includes rationals, which are your fractions, like 1 over 2, 2 over 3. You can actually see this as an example of type 1 divided by 2. You'll see that it's a fractional A. If you do type rational, I'm wondering if I can do that. What's a type constructor of rational again? Info rational ratio integer. Okay. Let's see if I can do this. Rational 1, 2. There is no data structure in scope. Perhaps you meant what? 2 rational. Okay. So some of these functions have constructors already built for them. Not entirely sure why I can't just call them. Some I've noticed in some code the constructor is the same name as a data declaration, and I'm never really sure if one is versus the other. We'll encounter that in some of the later examples that I've written down. I think I actually wrote this one down incorrectly. In addition to rationals, you have also our standard fixed point integers, which is also fixed point for real numbers. They're also called fixed precision. Basically, these are numbers that has a fixed number of decimal points. So you can actually say E2 or fixed E2 or fixed E3 or fixed E4, and those are the number of decimal points that this library kind of like, or this type of will allow you to match to, and it won't it'll round to the nearest upward number for those values that are uh, under or above a particular fixed point number. Then we have also scientific numbers, which is another way of dealing with um, arbitrary floating point precision numbers. Those are represented in using scientific notation. I encourage you to go look up scientific notation for more information, like 1E10, 1E5. Now, one thing to be aware of related to scientific notation is since the coefficient is stored using both an int and an integer, an int itself cannot be arbitrarily large. There's a range that you have for scientific, but you just be aware of that. Scientific actually itself is available. It's not available in the Prelude, but it's available as a library that you can find. That's in addition to the Preludes. Then after that, we have our standard floating point, which is single precision, and double precision floating point. Single precision also is a different way of dealing with fixed point number representations, which is why fixed can be used a lot more in a lot of like financial applications, whereas float is generally not encouraged to be used in like business applications, especially when you're dealing with dollars and cents and stuff like that, just because of the rounding problems associated with it and the sensitivity of those. Double is the same idea, same rules apply for double precision. These guys are you have some rounding rules that you need to deal with, and it's generally not useful for financial applications. All of these can compare. They have your standard okay. So there's one more thing I forgot to mention here before I go start talking about comparison. One is related to the Boolean data type, and another one is related to int specifically. So the Boolean data type, as you know, has true or false. We've explicitly listed them in our MyBool example as data constructors. For most numeric data types, unlike Bool, we don't have the data constructors written out, mainly because we're dealing with numbers, all right, and they're all going to be an infinite series, right? So you can't write every single one down. So so for numeric types, in terms of data constructors, just be aware that there isn't necessarily a proper data constructor for the type. It uses some GHC magic, some Haskell magic to go and construct the integer type and make sure that that's of that type. Just so that we don't have to figure out every possible value to have to go and put into things. The other thing that I want to mention is int. Regarding int, is that ints are basically machine represented integers, which computer hardware has supported for years. The one thing that you'd want to be aware of is that integer, well, int also has some sub types that are included in terms of type declaration. So like int 8 is one type of this, or int 16. Although these are rarely used, as you can see, because they're not even part of the prelude. But they are available. The one thing to be aware of is because you're fixing the size of the word that's you're fixing the number of values that can be associated with it. So you are going to be dealing with overflow and underflow accordingly. So these can be actually imported into your GHC by using ghc.int. And now if you do 127, let's say x equals, well, let's say 127 and it's an integer 8. You know that this can be represented as an 8-bit integer, but if you try to do 128, you cannot. You'll get an error saying that it tries to construct it because it's overflowed. Okay. This is just some stuff that you could be aware of. Although these are all defined in it, just be careful when you're using these just because of their finite ranges. You can also find inbound of info, the minimum and maximum bound of a value by specifying the type to the actual min bound and max bound. So, for example, if you wanted to min bound int, we know that this is the integer size that the minimum integer that it can be represented, which I think is 2 to the 64 minus 1, but I'm not entirely sure. I have to go and double check that. Maximum also is there. You also have you could also find the minimum and maximum bounds for all the other types. So like int, let's see, int 32, max bound for int 64 actually is what I wanted to check. Yeah. So in the case of int, it is a 64-bit integer. It's just representing the computer hardware of words. It is just to be aware of. It is something that that's around. You can actually go and query all these min bound, max bound. There are ranges associated with it and so forth. Regarding Word, it might be useful, especially when you're dealing with like binary values, to know that you're dealing with the word size, because word is usually what normally people use when they're talking about machine representations of ints. So in cases where you're dealing with, like, say, binary data that's being passed in, Word might be more expressive in terms of how you're defining your types. It has the same sort of ranges. You could get more information about what's Word and all the different word sizes by importing data.word. And data.word has Word 8, 16, 32, and 64. And again, each of these have the same sort of bounds as their counterparts, with the exception of the fact that their mins are all going to be 0. Their maxes are going to be different. So Word 8 is going to be 255. Because again, the reason why it's not 128 for folks is think that you now have an extra bit that you can actually go and increase the ranges, since we're dealing with unsigned integers. That first bit is no longer the signed bit anymore when you're dealing with unsigned. values. So you've increased it by 2. So you have 255. That's the maximum value for that. Obviously, max bound for word 16 is 2 to the 16 minus 1, or 65,535. And you can, verify these and so forth and use them accordingly. So with words, just make sure that you're using them in the appropriate place to represent some of the machine-oriented values. So fractional. Let's see. How do I? So talk about actually info fractional. So fractional is a type class that encompasses all these values, as you can see here. When we go in and do an info on fractional, you can see that there are a couple of things that it defines. Class num of fractional is going to be where a division operator is defined, a reciprocal operator is defined, from rational is defined, and so forth. This is kind of how you would actually determine what sort of properties are associated with the specific type. When we're using fractionals, one thing to note is, especially when it comes to rational numbers, it automatically converts the representation to when it's doing the division to the most to a fixed precision representation if it's fixed precision, or a float, depending upon what it's used. So as an example, if we actually allow 1 divided by 2 to be computed, it won't actually return 1/2, as you might be thinking. It will return 0.5. Okay, and that's because the fractional type class recognizes that this can be converted into another type, and it picks the most simplistic type that will account for all the different types of variations for the division operator. Obviously, this means in the same case, for the case of 4 divided by 2, it's going to give you a float number. If you actually go and ask for the division, the type of the relational, you'll see that it's a fractional type associated with it. Finally, just very quickly, for numeric types, all the common operators that we all love are available, the logical operators for comparing values. So let's say we have x equals 5, okay, available for us. We can go and do equality, all right? We can go and do less than, greater than, and if we're trying to do not equal, so equality is this, not equal is going to be different than any other language that you use too. Not equal is very close to how it's represented in math. If you remember, in math, there's always a equal sign with a forward slash across it. That's kind of the notation that they've adopted for not equal as well. So in this case, if we say not equal to 5, it's obviously going to be false because x is 5. If we do not equal to 4, it's going to be returning true because obviously it's not equal to 4. This is probably more intuitive, honestly, of the notations that I've seen, just because it follows strictly with the math notation, but that's just me. In terms of what's returned, you're seeing that it's creating essentially true or false, which are the data constructors for bool. And you can get the type information for any one of these by just using what we've used before, which is, less than or equal to. And these are the type signatures associated with our definitions. Notice the difference between what's being done with equality and what's being done with the other operators. They're taking an ORD type class versus an EQ type class, and these are two different type classes dealing with equality and ordered types accordingly. All right, they separated the two versions. So something being ordered doesn't necessarily mean that you're dealing with equality. but you should make sure that something has ordered inequality if and when you need it. Additionally, let's see, what else did I want to cover? You know what? It's already going over than I expected. I can quickly cover the last two topics, and we can touch base and make these a little bit more. We can dig a little deeper on this next time, but very quickly, um, not, so we've talked about already bools, and we've talked about the fact that expressions return to bools type using the data constructor. I also probably mentioned that about the not operator earlier. Bools are special because expressions that return to bools can be encountered in more complex expressions as well. For example, logical and, okay, and logical or are available for you to write very complex expressions. These things can take either the data constructor values themselves, like you're seeing here. I can use true in logical conjunction or logical disjunction in this case. Obviously, I can use true the data constructor in the not operator, but I can also use obviously the expressions that represent some of these. Okay, so I can do 8 is greater than 4 and 4 is less than 5. Obviously, this is going to be true because these expressions ultimately get reduced to their data constructed values, and then that ultimate evaluation will be based on the data constructed values. These are all to be aware of. These are all available for you. You can also write if conditionals, but if is very, very special because if is not a statement in Haskell. Okay, if is an expression in Haskell. That means the conditional if then else essentially gets evaluated at once. It doesn't generate necessarily any particular code. You could think of this as if you've written a lambda expression. You're invoking a function that will actually go and evaluate this if conditional. A good example of this is let's say that we have couple of strings called truth and false being called lie. And if we use, say, an expression here, if true, then t, else false, this ultimately evaluates the expression to truth. And obviously that makes sense, right? So if we do also this, true, else false, so we get a lie. And if we do a type on this guy, and this is the most important thing, to look at this expression's final type when it gets evaluated, okay? And, oops, I may have done this wrong. Yeah, sorry, this. Okay, so here you could see that this is an expression because on the left-hand side we were saying that the final value of this, and remember everything is an expression in Haskell. There are no such thing. There isn't. I haven't actually seen statements yet in any sort of shape or form. This expression will always be represented on the left-hand side before the has type. So this is before evaluation. It figured out that this is going to return a list of characters. Okay, This is particularly important because folks who encounter this think that this is a series of statements, and it's not. It's actually a single expression. It's a series of expressions that will ultimately get reduced at the time that it gets compiled. It's a little uh, uh, screwy for folks, but you if we actually look at how it reduces, we're just doing substitution essentially, and we're reducing the expression every time using it's a variant of beta reduction essentially. So in this example here, if we have, let's say, we change this guy here, this example to if 4 is less than 5, then T else false. Okay, what this is happening, or even better, let's say x equals 1. Okay, if 4 plus x is less than 5, then T else f. Okay, here we're just going to be doing beta reduction, right? X gets substituted into this in this value, so we then get if 4 plus 1 less than 5, then T is less than or else F. And that gets reduced, obviously, to, since those are in parentheses, that takes precedence to 5 less than 5, then T else F. And since that expression there is taking precedence over the logic because we haven't reduced to something that the if expression can execute yet, so we're going to run that again, and since 5 is less than 5 is obviously false, we get this final expression, and now the expression is ready to be evaluated, and we'll actually go in and pick the branch based on the Boolean value that was returned. Okay, it'll do a lookup saying, oh, wait a second, false is in the second, is the branch, is the else branch, let's go and look in there. Okay. If you're wondering if you need to put an else, I've thought about this too, but I haven't actually tried this out. A lot of examples that I've seen always required an else, but we can try this. If false, then T. You can see that this is an invalid expression because there's no else condition associated with it. So you need to have, when you're dealing with ifs in these conditionals, you need to provide both the true execution and the false execution. The if else has to be there. Otherwise, it will not actually work as you expect it to. Let's see here. Then finally, I just wanted to touch base on. You know what? I'm going to stop here because the last two sections I don't want to rush through. These are on tuples and lists. So next time we're going to finish off tuples and lists, our coverage of tuples and lists, and we're going to go into how to construct, how to deal with currying, polymorphism, and the basics of type inference, and how to read type signatures much better than what we're currently doing today. Are there questions? I know that this was a lot. I apologize for going way over, but this is a lot of important material to get through before we start getting a look at the interesting stuff. Okay, if there aren't any questions, thanks for joining me. I'll see you guys next week. I will post a meetup shortly after. I hope you guys can join us. Please like or subscribe, like our videos, and please subscribe to our channel for getting more updates for Atlanta functional programming videos. Thanks for joining. See ya.